go back to where we were. We had just started talking about the phase speed, I think, of a traveling wave. And here I'm imagining we're looking at the classical wave equation in one dimension. So this is modeling like wave motion in a guitar string in one dimension. And one of the reasons we call it a wave equation at all is because there's a traveling wave solution. That means some sort of sinusoidal or wave that has a definite wavelength that travels at a constant speed. So the peaks and valleys move to one side or the other as time goes on. And one of the things we figured out was it makes sense to write the phase speed, intuitively it moves one wavelength in one. But if we express that, let me close my email so I don't keep getting updates there. If we re-express lambda and t in terms of omega and k, the phase speed, as you've learned before, is omega over k. So when we write our traveling wave in this form, a constant times the cosine of kx minus omega t, or the sine of kx minus omega t, it travels to the left or to the right, depending on the sine of omega over k at speed omega over k. Okay, now, just because one wave travels to the right at one speed doesn't mean that all waves of different wavelengths travel at the same speed. And I think where we left off last time was saying the word to describe different wavelengths traveling at different speeds, having different phase speeds, is dispersion. And a dispersion relation is an equation that's going to tell us how the phase speed depends on wavelength. And usually for convenience, instead of specifying wavelength, since k is 2 pi over lambda, we usually write it as a function of k rather than lambda. Okay, so the way to, I'm assuming you found dispersion relations maybe before, but it's worth reminding yourself. Usually you have to see these things like 3 times before they start to stick. To find a dispersion relationship, what you do is take your wave equation. So we had our classical wave equation, which I don't have on this slide right here, but you substitute in the generic form for a traveling wave. So you could either just put a cosine in or a sine of kx minus omega t, or you could put the whole mess in if you really wanted to work hard. And then force it to satisfy the wave equation. In other words, if we choose the constants a, k, and omega correctly related, then we'll find that it satisfies the wave equation. Otherwise, it won't. Okay. So to find the dispersion relation for the classical wave equation, we would substitute this expression, or even just the cosine part of it, in and see to make the left-hand side and the right-hand side of the wave equation equal, k and omega have to be related a certain way. And we already saw what that was before. If I go back to our worksheet that we worked on before, or at least I worked on and you looked at, we found out when we substituted that cosine function into the classical wave equation, here's the left-hand side, here's the right-hand side, they're not going to be equal unless omega squared equals c squared k squared. That is the relationship between omega and k, and that is our dispersion relation in disguise. And so we're going to see this coming back later because we're going to be concerned with the dispersion relationship of the time-dependent Schrodinger equation. Now, in order to see what that says about phase velocity, a lot of times it's convenient to solve that relationship between omega and k just for omega over k on one side. So I'm going to solve for what we already found out is the phase speed or phase velocity, omega over k. And if I go back to this here, if I solve for omega here, I get, if I take the square root of both sides with the plus or minus sign, I get omega is equal to plus or minus ck. And if I solve for omega over k, the magnitude of the phase velocity or the phase speed is going to be c, or the phase velocity is plus or minus c. So that means for the classical wave equation, all of the waves travel either left or right, and they travel at the same speed. It doesn't matter what wavelength we're talking about. If I make a large wavelength wave travel along a string or a small wavelength one, at least if they satisfy the classical wave equation, they all travel at the same speed. In other words, it's dispersionless. Okay. Now, let's try it. So that was the demonstration of the classical wave equation. And again, you're seeing a lot of abbreviations I'm using here, CWE for classical wave equation. I'm not going to keep doing that the whole semester, but there are a few things that we keep writing over and over again, like time-dependent Schrodinger equation. I'm going to write as TDSE because it's very tiresome to write that on the board. So CWE means classical wave equation, the one you presumably saw in 240. Okay, so let's look at the worksheet. And again, I'm hoping that you still have the email that I sent to you yesterday with that PDF of the worksheet that we were working our way through. And I'm looking at problem 2 here, which is under the heading of dispersion. There's a long preamble, and this is just talking about what dispersion means, but the problem starts down here. We showed that the phase velocity is omega over k. And here's a different wave equation. And in fact, I'm going to alter this because it comes out a little bit nicer. So this is not the classical wave equation. You'll notice there's a fourth derivative on this side. But I actually want to do the example where instead of the x derivative being a fourth partial derivative, let's make it a sixth partial derivative. The fourth partial derivative doesn't quite work out with the traveling wave solutions. So this is very similar to the classical wave equation, except having a second partial derivative on this side, we're going to make it a sixth partial derivative on this side. And it turns out it still has traveling wave solutions. For every k, there's going to be a traveling wave solution. What we want to find out here is how do k and omega have to be related? And what does that tell us about how the phase speed changes with k or changes with wavelength? So if I go to my solution here and go down, again, I'm altering, I wanted to alter this and I forgot to change it, but here's what I wanted to change it to. Instead of the fourth derivative, let's do the sixth derivative. It's not obvious that there will be traveling wave solutions, but if I substitute this generic form for a traveling wave solution, cosine of kx minus omega t, the left-hand side, that time derivative is the same as it was before. And the right-hand side now has this sixth partial derivative with the alpha squared out in front of it. Alpha is just a constant here. So the alpha squared comes along for the ride. When I take the two derivatives of this, the cosine is going to turn into a minus cosine, and I'll get a factor of k squared out in front. So I'll get minus k squared. When I take two more derivatives, I'll get another minus k squared, and two more derivatives, that gives me another minus k squared. So overall, I will just get a factor of minus k to the sixth coming out from all those chain rule applications. So if the left-hand side and the right-hand side are going to be equal, in other words, if it's going to satisfy this other wave equation that I've just made up here, we're going to have to require that omega squared equals alpha squared times k to the sixth. And that is a dispersion relation. It's a relationship between omega and k. And in order to think of it in terms of phase speeds, conventionally, we usually solve for omega over k. This is still a dispersion relation, but it sort of makes more sense to us in terms of wave speeds if we solve for omega over k. So since I have an omega squared on this side, I'm going to divide both sides by k squared and then take plus or minus the square root of everything. And I get that omega over k is plus or minus alpha times k squared. So if we think of the magnitude of omega over k as the phase speed, that's how fast those peaks and valleys move to the left or to the right. The plus or minus is telling us whether it moves left or right. And it increases with increasing k, right? As k gets bigger, omega over k gets bigger. So the question that's being asked at the bottom here is the phase speed larger for shorter or longer wavelengths? What is this telling us here? Somebody unmute and help me think about that.
faster for longer wavelengths.
Faster for longer wavelengths. So we have to think about that lambda is inversely related to k. So notice as k increases, the right-hand side is going to get bigger, and that's going to make the phase speed bigger. So for bigger k, we have a bigger phase speed, but then lambda is inversely related to k. So that's going to correspond to shorter wavelengths, which I think is the opposite of what Jake said, but it's easy to sort of get confused. Sometimes I think, I often think shorter wavelengths corresponds to higher energy. And sometimes I get those confused because we've already worked into our brain from, optics and from modern physics that short wavelengths is higher because it's higher energy radiation, but it's actually a shorter wavelength or a smaller wavelength. So in this case, as the wavelength gets shorter and shorter, tighter curls or tighter up and down kind of oscillation, they travel faster. Okay, and that's dispersion. Okay, the important part for us to remember for later on, we're going to find the dispersion relation for the time-dependent Schrodinger equation. I apologize, I'm not going to have a lot of abbreviations for the whole term, but we do use the term time-dependent Schrodinger equation. We're going to find it in exactly the same way. And in fact, I'll write it down shortly. But to do it, what we do is write down the time-dependent Schrodinger equation. If we put the potential energy as just 0 in there, it will have traveling wave solutions, and we can figure out a dispersion relation. We'll find out that it has dispersion. It's not dispersionless, just like this wave equation that I made up here has dispersion. It's not dispersionless. Okay. Let's go back to the slides now. Any questions on that? No, says Alvis. Okay, great. So we found out from the previous work we had done, the classical wave equation is dispersionless. We found out the made up wave equation. I'm calling it a wave equation because it has traveling wave solutions. I made up a different one. We found out it had dispersion, the one with the 6th partial derivative in it. Omega over k depended on k squared, so it changed with wavelength. So I'm going to summarize in just a second, but the next thing we're going to head to is that, especially in quantum mechanics, there's a more convenient way to write these traveling waves in terms of complex exponential functions that you may or may not have seen before. Probably Dr. Neiser talks about complex traveling waves in physics 240. Anybody either give me a thumbs up or thumbs down on that for the people I can see? Yes. So he talks about e to the I kx minus omega t, or e to the minus I kx minus omega t. But because it's not something you've learned in a lot of math classes, it's worthwhile at the beginning just reminding ourselves about those functions. They can seem a little bit off-putting. So that's where we're heading. And I guess I sort of meant to start with, this is a big review of everything that we were talking about so far. It just to bring us back, and I sort of meant to start with this today, and somehow I missed these review questions. So the ones that are grayed out here, let's just talk them through, make sure we're seeing what the big picture is. We started out talking about problems with the picture of matter made of point particles interacting by electric forces. We might naively think of a chunk of sodium chloride as being just something that's somehow stable, but we found out from Earnshaw's theorem, which is pretty easy to prove, using, you'll find the proof in Griffith's book for upper level E&M, that it's unstable. It doesn't matter how you try to pin things in, it will be unstable under slight movement of the particles. So there's no such thing as a stable sodium chloride crystal. And there was also a problem with the stability of matter because it radiates things away. If we at least think of it as point particles, the electron orbiting the proton. So there are some problems there, which at least motivates why we might want to go to waves. It's not clear yet why waves solve the stability problem. And a few of you asked why, I think in your reading responses, it does solve the stability problem. And we will find that out as we go along, how the waves, but the idea is there are wave solutions that just sort of sit there and oscillate, and they're going to replace our idea of an orbiting electron around a proton or around a nucleus. What's the key difference between a solution to an ordinary differential equation? That's like your math 360 kind of thing that you study, and a partial differential equation. Yi-Chen, what's the difference between a solution to an ODE and a PDE?
I don't like, you mean the difference in solution for OD and PD?
Yeah, when I'm looking at a solution, how would I know that I'm looking at a solution to a PDE versus an ODE when I'm just looking at the function that's being given as a solution?
Well, I think it depends on the variable, right? If it's OD,
Yes.
then it's only have one, and PD you may have couple, right?
That's right. So we would expect, for the Schrodinger equation, it's a partial differential equation. We're going to have our psi as a function of x and t, or maybe x, y, z, and t. And therefore, we have lots of partial derivatives we can take, okay? And I'm just emphasizing that. I know that's straightforward, but since you don't take a class in PDEs, it's worthwhile just remembering that's the only difference. But what a difference it makes. Partial differential equations are way more difficult to solve than ODEs. And there are lots of open problems in mathematics in the field of partial differential equations. That's a huge area of study in usually what's called applied mathematics. What does the superposition principle mean for the classical wave equation? Makai, you want to take a stab at that? What does the superposition principle mean?
Any two solutions to the classical wave equation, any linear combination of those two solutions would also be a solution.
Right. So that sort of answers the next problem too. So usually, I don't know, maybe I'm using the terminology slightly different than maybe people normally do, but usually the superposition principle, people generically mean you can take the sum of two solutions and it's a solution. Just like we saw those pulses going through each other by adding together in the GIF that I showed. More generally, the property of the classical wave equation that lets us know that its solutions obey the superposition principle is that it's a linear partial differential equation. And linearity means any linear combination of solutions is a solution. And the superposition principle, well, if you add two things together, that's a very specific kind of linear combination. So the superposition principle and linearity are almost the same thing. Linearity is just a little bit more general. Alvis, are traveling wave solutions the only solutions to the classical wave equation?
Okay, admittedly, this is more intuition, but I'm thinking no. That it's not the only, so that they're not the only solutions.
That's right. They are very special solutions, ones that have peaks and valleys just moving along uniformly. But just like, when you look at the surface of a swimming pool, you don't tend to see nice regular wavelength waves traveling in one direction or another. It's some random wiggling and jiggling of the surface of the pool. Similarly, if you have a guitar string, if you pluck it, it's not exactly a random kind of initial condition. But if you were able to shape that string into some initial shape that wasn't particularly special, just take some random initial shape and then let it go, you would find that guitar string just vibrates in some weird kind of random way. It obeys the classical wave equation, but it certainly it's not going to look like a traveling wave with a well-defined wavelength. There's no wave you're going to see in it. So traveling wave solutions are very special solutions, but they're going to be important to us. The same thing's true with the time-dependent Schrodinger equation. We're going to find there are traveling wave solutions. They're not nearly all of the solutions, but they're going to be very particular and important ones to us, at least for the free particle time-dependent Schrodinger equation, where the potential is zero. So a particle that's not subject to any potential energy function. Okay, now just back to what we were talking about. What does a dispersion relation tell us? Riley, you want to tell me what that means?
It tells us the equation of how the phase velocity depends on the wavelength.
All right, so dispersion means that the phase velocity somehow depends on wavelength, and the dispersion relation tells us exactly how, although conventionally people like to express it as a function of k rather than lambda, but intuitively it makes more sense in terms of lambda to human beings, I think. What is the dispersion relation for the classical wave equation? Tanner, you want to help me with that one? What is omega over k equal to there?
Omega over k.
Yeah, in other words, what's the phase velocity equal to?
Lambda over t.
Well, it is equal to lambda over t. That's not exactly what I was getting at, but you're right there. For the classical wave equation, the dispersion relation we got was omega equals plus or minus ck, which solve for omega over k. Omega over k, or the phase velocity, is plus or minus c. And that means that irrespective of wavelength, every traveling wave travels to the left or to the right at c. Now, in this context, c is the speed of the wave on that particular medium. So if we were talking about electromagnetic radiation, c would be the speed of light. But if you have a particular guitar string that's under a certain amount of tension and has a certain density along the guitar string, c would be the wave speed on that string. And if we're talking about sound waves, it would be the speed of sound waves in air, at the particular density and temperature that we're talking about. So in this case, if it satisfies the classical wave equation, that means that omega over k is constant, or at least the magnitude of omega over k is constant. The speed is constant. The direction, of course, could be in one dimension, either direction. Okay, and what does the phase velocity tell us about the traveling wave? I'm not going to belabor this, but it tells us how fast it's going, or at least how fast and in which direction it's traveling. Okay, so I was saying, back to our, we were going to do 5 things at the beginning of this kind of introductory material. I was saying that we've been talking about traveling wave solutions to the classical wave equation, and also we want to think about them in terms of the time-dependent Schrodinger equation coming up. And we've been thinking of them as cosine or sine of kx minus omega t. It turns out that's not going to work out so well for the time-dependent Schrodinger equation for reasons we'll come into, but for the classical wave equation, there's just a different but completely equivalent way of expressing traveling waves, and it relies on something called Euler's relation, which, I don't know if you learned it in any of your math classes. You probably learned about it in Physics 240, but it's worth reviewing. Euler was a really bright guy, as you know, his name's on a lot of things, and when you say Euler's equation, there's probably 4 different things that are called Euler's equation, but this is one of them, and no less important than the other ones. The other ones are in lots of different fields of mathematics, but this Euler's equation says that e to the I theta equals cosine theta plus I sine theta. Okay, so this kind of, if you like, defines what this complex exponential function does as a function of theta. And it's got an I in there, so it's going to have a complex output if theta is real. We're always going to take theta to be real. It's going to be like an angular kind of variable. So let's think about how to justify this. I'm assuming, wherever you heard about this before, if you have, does Dr. Neiser talk about Euler's equation in Physics 240? Thumbs up or thumbs down? Yes, he does. Okay, good. So you've seen this before, but let's just remind ourselves where it comes from. Here's how we justify it. I don't remember many Taylor series expressions from calculus, but the one I do remember, and it's worth remembering, is the Taylor series for e to the x. Can someone remind me what the Taylor series for e to the x is, if you've got it burned into your brain somewhere? Just unmute and you can say it.
1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the 4th divided by 4th factorial plus et cetera, et cetera, et cetera.
Right. So that's one I remember, just because there's not too many complicated coefficients to remember in there. Whatever the power is, you divide by that factorial function, and that's the Taylor series for e to the x. So to justify this, what we're going to do is write down that Taylor series. We're going to do this on the worksheet in just a second. And then because we have the Taylor series for e to the x, we're just going to substitute for x as I theta. Substitute I theta everywhere there's an x into a series. Now we're going to have x squareds in there. So we're going to have I squared theta squared. And we know that I squared is -1, right? Imaginary constant number. I times I is -1. So we can use that to simplify the series. So let's go back to our worksheet here and go on to the next one. Here's what Alvis just told me. E to the x is 1 plus x squared over 2 factorial, and so on. I did it up to x to the 4th over 4 factorial. And then everywhere there's an x, I'm going to substitute x equals I theta. So I get an expression for not e to the x, but e to the I theta. So when I substitute that in there, I get 1 plus I theta squared over 2 factorial plus I theta cubed over 3 factorial. And of course, I'm going to write this I squared theta squared as minus theta squared over 2 factorial. And this I cubed I can write as I times I times I, and I squared is -1. So this would be minus I times theta cubed over 3 factorial, and so on. So when I simplify that, here's my Taylor series for e to the I theta. And now, let me just go back to the slides. That's parts A and B, I think, of the worksheet. We've simplified each term. Now what I'm going to do is separate this out into a sum of 2 series. You'll notice that every other term has an I in it, and every other term is real. So what we're going to do is separate out the terms with the I's from the ones without the I's in it, and we'll factor out the I there to justify this relationship. So I'm taking this series that I got right here, and I notice the first, the third, the fifth terms are all real. So let's put those out here. They don't have any I's. I'm going to group them all together. And then the second, the fourth, and the sixth term are all complex. They all have an I out in front of them. I'm going to group them together, factor out the I, and then I'm going to try to recognize what this series is here and this series. And, you know, not to belabor the point, I sort of half remember the Taylor series for cosine and sine have these, they're alternating terms, and they only contain even powers or odd powers for the sine. So this thing in parentheses right here is exactly sine of theta. And this thing in the first parentheses is exactly cosine of theta. So this is saying e to the I theta is cosine theta plus I sine of theta. Okay, we're not going to be using these Taylor series in any way on a daily basis, but it's just good to know where it comes from. So we've justified that e to the I theta is cosine theta plus I sine theta. Any questions about that little mini derivation there that I would have forced you to write down and go through in class, but I'm sort of going through it together here. Okay, now, so that's one example of Euler's equation. There's another related one, which is an expression for e to the minus I theta, which is cosine theta minus I times sine of theta. Can anybody think of how to justify that without going through the whole process? Of course, we could imitate what we did up here and repeat all that work, but we don't really need to justify this one once we've already justified the one up at the top. How could we easily get this lower one, the expression for e to the minus I theta, from it? Anybody just volunteer, unmute if you have an idea of how to immediately get from the top relation to this expression for e to the minus I theta, if we've already got an expression for e to the I theta.
You just substitute negative I for I, right?
Yeah, so one way to think about it, and yeah, I'm going to emphasize a slightly different way, but you could say, let's take the complex conjugate of both sides. That's another way for saying what I think Jake was the one who came on there, said. And it looks, so I just look on both sides and I say, everywhere there's an I, I'm going to replace it with a minus I. If two numbers are equal, this is saying this number is equal to this number, then their complex conjugates better be equal too. Now, the only thing that might give you some pause there is you might think, well, there's some notation here for some exponential function, and maybe there's an I hidden inside the functional notation. Just because I replaced the I with a minus I, am I really sure that I'm taking the complex conjugate of this side? Or maybe somehow in the functional notation, there's something else. But a slightly different way of doing really the same thing is just to replace theta by minus theta. So notice if I have a function, I can always replace the argument of the function with the negative of the argument of the function and try to simplify it. And it comes to the same thing for what Jake was suggesting. So going on, if doing it my way, if I replace theta by minus theta, right? If I've got a function of x equals some other function of x, I can replace x with minus x, just insert a new argument in for x. As long as I replace all the x's that appear, we're good to go. So if I replace theta with minus theta, it comes to the same thing Jake was saying. Then I get cosine of minus theta on the right-hand side. And since cosine is an even function, that's equal to cosine of theta. And sine of minus theta, and since sine is an odd function, that's equal to minus the sine of theta. And therefore, e to the minus I theta is cosine theta minus I sine theta. So we might call that Euler's relation too. It's essentially the same thing. Okay. Finally, one thing that's very useful is to be able to write, we've got e to the I theta and e to the minus I theta written in terms of cosines and sines. Can I now express cosine and sine in terms of e to the I theta and e to the minus I theta? How might I use these two relationships, the e to the minus I theta Euler relation and the e to the I theta one, to express cosine of theta in terms of those two complex exponential functions?
Plus them together and divide by 2.
Yeah, I mean, the same way we always saw, I've got this solved for the exponentials, but, if I add these two equations together, I can see I've got an I sine theta and a minus I sine theta. They're going to cancel out and I'll get a 2 cosine theta on the right-hand side. So if I add them and divide by 2, let's go back to my solution sheet. I think that's the next thing on here. So if I add them, I get this relationship, and then I divide by 2. I can write cosine of theta this way. Similarly, if I subtract them and then divide by 2i, I get this expression for sine of theta. And so that's saying cosine of theta and sine of theta can be expressed as a linear combination of these two complex exponential functions. Okay, whatever. We'll see how we'll use that in just a second. So when we say Euler's equation in this context, any one of these 4 relationships that we just found could be called Euler's equation. They're all very closely related to each other. Once you've justified one of them, the other ones are really easy to get. So they're almost the same thing. All right, so what's the point of this? Well, we were saying that what makes something be called a wave equation? In other words, why are we going to call Schrodinger's equation, at least with 0 potential in it, a wave equation? The reason we're going to do that is because it has traveling wave solutions. And so far, we've been talking about, at least for the classical wave equation, we wrote the traveling wave solutions in this way. We want to re-express those in terms of complex exponentials, right? I now know how to write a cosine in terms of e to the I something and e to the minus I something, and similarly. So since cosine of theta is e to the I theta plus e to the minus I theta over 2, cosine of this mess is, can be expressed this way. And I can similarly express sine that way. And therefore, I could rewrite this traveling wave solution in a completely equivalent form by, solving for what coefficients C and D have to be. I could say, it's up to me. For the classical wave equation, I could either write this as the most generic traveling wave or this as the most generic traveling wave with arbitrary coefficients out in front. And if we chose the coefficients A and B down there, we could solve for what C and D had to be there. So it's your choice with the the classical wave equation. You can write the solutions either as cosines and sines or as a combination of complex exponentials. Okay, so what? Well, it's going to come to something when we talk about the Schrodinger equation shortly. Okay, we're going to call these things, even though they're not sines and cosines, we're still going to call this e to the I kx minus omega t and e to the minus I, that same function, as traveling waves. They are a kind of wave. They have a wavelength, and it's equivalent to this kind of expression. It's just recasting it in a different form. That has the same dispersion relation. Remember, the dispersion relation, if we're talking about the classical wave equation, it only depends on the partial differential equation. It doesn't matter how we write the solution. So it's not affecting the dispersion relation. If we're talking about the classical wave equation, the dispersion relations is still omega over k is plus or minus c. Okay, so going back to my summary of the properties, we could write the traveling wave solutions this way for the classical wave equation or this way. Okay, now, how do I envision these? And maybe you talked about this in your waves course too. I know how to envision cosine and sines as traveling waves. You just have peaks and valleys going this way or that way. But what about these complex exponential functions? We can visualize them if we work hard enough. We won't always do this because it requires a little bit more artistry than normal. It's related to the idea of how do we graph the function e to the I theta, right? I know how to graph the function e to the x. Here it is graphed here. I plot the input variable on the horizontal and the output on the vertical, and I get the graph of e to the x. But how do I graph e to the I theta? Well, it's got complex outputs. And so in general, I'm going to need 2 dimensions to graph a real function of a real variable. If I'm going to have complex outputs, I'm going to have to change how I think about it. So if we have a complex function, I'm assuming you guys have seen something like this before, but plotting in the complex plane, if I've got not a real number, but a complex number, usually it can be written in standard form as a real number plus I times another real number. That's the most generic complex number. And just like we plot real numbers on the real number line, we plot complex numbers conventionally in the complex plane. Okay, so A is called the real part of this complex number. B, which is another real number, is called the imaginary part of that complex number. And conventionally, if we want to plot this, we have to plot it in a plane. We plot the real part on the horizontal axis, imaginary part on the vertical axis. So if I wanted to plot A plus IB, I would plot it as a point in the complex plane. And therefore, if we want to plot this function e to the I theta, we have a real input, theta is a real number, but we have a complex output. E to the I theta is going to be a complex number in general. So we need a input axis going here, but the output's going to have a full complex plane there. So we're going to plot it kind of in 3 dimensions. And if we plot it, well, let's get some data. We already know from Euler's relation, this defines what e to the I theta is. So let's increase theta, starting at theta equals 0 and go up by 45 degrees in each step and see what it does. I know how to calculate cosine and sine of theta. So for 0, cosine of theta is 1, sine of theta is 0. In the complex plane, that's here. For theta equals pi over 4, cosine of theta is going to be 1 over root 2 or root 2 over 2, either way you write it. And same thing for sine of theta. And so the way I'm going to plot that number, root 2 over 2 is 0.707 approximately. So plotting that complex number at theta equals pi over 4 goes there. At pi over 2, it's completely imaginary. It's just 0 plus 1i and so on. So it keeps spiraling around as you go. So here we are at theta equals pi. As you go to 2 pi, it's going to go around here. And then to 3 pi, it goes over here. It keeps spiraling around as theta increases in the complex plane. So to plot this function, we need to display the theta axis increasing in this direction And then the output of the function is going to spiral around like a corkscrew around that axis. Just to display that, it's probably easier to do it in MATLAB. So I just cooked up a little function here. Let me move this down so it's out of the way. Here's a graph of e to the I theta as a function of theta. So theta is this axis right here, going in that direction. Here's the real output and the imaginary output on the vertical. And if I, rotate it just so that we can see the 3D aspect of it, it's spiraling kind of in a right-handed way around the x-axis, the theta axis in that case. And if I wanted to plot e to the minus I theta, the only difference is instead of spiraling up and around as theta increases, it spirals down and around. So if I plot that, this is e to the minus I theta shown in gray there. Instead of spiraling around this way, it spirals the opposite way around the axis. So if pressed, we know how to think about these. And I guess I should say that there's a definite wavelength to this function. Even though it's a complex function, I can see that the distance along the theta axis from there to there is the wavelength of this function. Okay. Just cancel that and go back here. So e to the I theta spirals around the theta axis, and therefore we're going to be concerned with e to the I kx minus omega t. E to the I x spirals around the x-axis, if you like. What about e to the I kx? Suppose I choose k equals 3. If I have a graph of e to the I x, how is e to the I 3x going to change? Jake Woosley, you want to weigh in on that?
You're asking again if it doesn't equal 1.
Yeah, what would we see differently? In other words, here's a graph of e to the I 1 times x, right? This is e to the I x as x increases, right? I was writing it as theta, but this could just as well be x. And it goes through a complete period as theta or x goes from 0 to 2 pi. What if I, instead of plotting e to the I theta or e to the I x, I plotted e to the I 3x? What would we see different about this function?
Would it shrink in terms of
Yeah, it's going to become a more tightly curled corkscrew, right? By a, the wavelength is going to become 1/3 of what it was before. And let me cancel out of this and actually change the code here. See, and go back to my code. I put a parameter k in there that I can change. So let's change k to 3 and run it. And hopefully we can keep in our mind what it looked like before and how it's changed. It's more tightly curled than it was before, right? The wavelength has gotten smaller. The spatial frequency has gotten larger, if you like. Okay, so that's what k does there. Oops, I forgot I need to cancel out of there. Let's go back to the slides. Okay, it has a different wavelength. Bigger k means a smaller wavelength, as we already know. So, this isn't wiggling and jiggling in a real sense, but it's wiggling and jiggling by corkscrewing around the x-axis. All right, now we're concerned with these traveling waves, e to the I kx minus omega t. We've been considering maybe omega equals 0. In other words, we were just talking about e to the I kx if omega is 0. But if I let that omega be some non-zero, say positive constant, what's going to happen to that graph as time goes on? Gracie, do you have any idea what's going to happen to the graph of e to the I kx if I replace it with e to the I kx minus omega t for some positive omega and let t increase? What's the graph going to do as time goes on?
don't recall. No.
So what I'm referring to is something that we learned back in high school when you were talking about transformations of graphs, right?
Yeah.
If I've got a function cosine of x and I replace the x by x minus 2,
It shifts
probably
to the right.
it translates it in the positive direction by 2. And so I've got a graph of e to the I kx, and I then subtract off some constant here from kx. I could factor out the x so we could see exactly what's happening on x. But essentially, it's going to cause it to translate in the positive direction. If t is positive and omega is positive, right? Then as t gets bigger and bigger, we're going to subtract a larger and larger constant off of the variable we were plotting against before. And that's going to cause it to translate in the positive direction. I guess the way you're looking would be like that. Let's look at that. So it's going to translate it as time goes on and translate it further and further to the right. And the bigger omega is, right? If omega is larger, then as I change t from 0 to 1 second, then the number we're subtracting off is going to be larger and larger, and that's going to cause it to translate at a greater rate. So let me show you a different MATLAB kind of thing. It's going to translate the same way those cosines and sines translate to the right. Let's see if this works here. So here I've got e to the I kx minus omega t, and I'm letting t increase. In some sense, it looks like it's spiraling around the axis, but you'll notice it makes just as much sense to see it as moving in the positive theta direction. I guess I should have, I'm writing x here. I should have labeled this as x right there, but it's translating to the right. So that's a moving or traveling wave solution. And so it's in that sense that we can think of this as a traveling wave solution. And that justifies anything that has this as a solution for all different k values, for different wavelengths, we're justified as calling a kind of wave equation, not just the classical wave equation, but anything else that has that kind of solution, okay? So just to summarize again, for the classical wave equation, it's important properties, it's linear, that's related to the superposition principle. It's for each wavelength, for each k value or for each lambda, we have traveling wave solutions. It's dispersionless, and it's important to keep in mind down here in blue that the traveling wave solutions are very particular ones, but more generally, there's going to be solutions that don't look at all like traveling waves, but these are just sort of more convenient ones. And it's because there are traveling wave solutions that we tend to call this PDE a wave equation at all. Okay, so let's go on where we want to make connection now with the Schrodinger equation. We know it's a kind of wave equation, or at least de Broglie was the one who said it had wave-like solutions that we could think of. Okay, so there are lots of PDEs referred to as wave equations. What they have in common is that they've got to have traveling wave solutions for each wavelength or for each wave number. Each wave number is equivalent to a wavelength. So if I can find a solution of this form for each k, or a solution of this form for each k, or one of these complex exponential traveling waves, we would tend to call it a wave equation, that particular PDE. Okay, so that's what they're going to have in common if we're talking about PDEs that we give the word or label wave equation to them. But they might have some differences. We know already that one difference is that they might have different phase velocities as a function of k. In other words, their dispersion relations might be different. So that's one possible difference between them. Another possible difference is that some wave equations can be nonlinear, so they don't satisfy the superposition principle. In other words, if two pulses are coming at each other and those pulses happen to be solutions, when they pass through each other, they would be altered by each other and they would be, somehow changed after they pass through each other. That would be a property that would be a property of a nonlinear PDE. Even if there are traveling wave solutions, it might be nonlinear. Now, we're not going to talk about nonlinear PDEs because, like the classical wave equation, the time-dependent Schrodinger equation is linear, so we can rely on superposition principles, but that's one other possible difference. Okay, so now let's start. We've built up a little bit of intuition or reminded ourselves from Physics 240, some intuition about the classical wave equation. Let's now compare to the time dependent Schrodinger equation. That's what you just call the Schrodinger equation in modern physics. It's the one with the partial derivative with respect to t of psi on one side and the second partial derivative with respect to x on the other side. Okay. I'm going to consider the case again of the free particle time-dependent Schrodinger equation. That means I'm going to set the potential equal to 0. So it's modeling a particle moving in 0 potential energy. So it's a free particle. It's not subject to any forces. Here is the classical wave equation. Here is the time-dependent Schrodinger equation with v of x set to 0. What are some similarities? Well, they're both wave equations. We haven't proved this for the time-dependent Schrodinger equation, but we will be able to show that there's a traveling wave solution for every wavelength. It turns out the traveling wave solutions in the time-dependent Schrodinger equation have to be complex traveling waves. Because of this I that appears over here, there's no real solutions to this equation. They're all inherently complex, so the cosines and sines aren't going to work as traveling wave solutions. Okay, they're also both linear. It's not clear, but you could, the same way we prove linearity for the classical wave equation, you could show that for the Schrodinger's equation too, right here, that if you have two solutions, any linear combination is a solution. There are several differences. The important ones for us are, first of all, they have different dispersion relations. We showed that the classical wave equation is dispersionless. The phase speed doesn't depend on k, whereas if you do the same thing for the time-dependent Schrodinger equation, the phase speed depends on k. It gets bigger as k gets bigger, or as the wavelength gets smaller. So it has dispersion. Another important thing that we haven't talked about yet is that this is an equation that is first order in time. In other words, the time derivative that appears in the PDE is a first order time derivative, whereas in the classical wave equation, it's a second order time derivative. And that has important consequences that we're going to see right away, or at least, excuse me, in chapter 2 of Griffith's book. So it comes up right away. And, you know, without thinking about that, maybe you relied on that in modern physics when you talked about solutions. Okay, so let's talk about partial differential equations that are first or second order in time. And I'm going to just immediately relate it to something you learned about in your ODE class, Math 360 or 361, whichever one it is. We're going to learn a procedure. And in fact, you saw this procedure in modern physics. You may have seen it in the waves course. If you were in physics 350, we did it in there. It's a procedure for solving partial differential equations. It's called separation of variables. And it allows us to turn a partial differential equation into a set of kind of related ordinary differential equations. So for the time-dependent Schrodinger equation, we have to, if we're doing separation of variables, we have to solve the ordinary differential equation, h bar times the ordinary derivative with respect to t of some unknown function is equal to a constant. So this capital T is just a function of time. This is called a first order ODE. Whereas for the classical wave equation, when we do separation of variables, we get a second order ODE. Okay, what do we know about first order ODEs and second order ODEs? Just quoting from your memory from Math 360, whatever it is. If you have a second order linear ODE, the general solution is a linear combination of two linearly independent solutions, right? And you had specific techniques for finding these in general, homogeneous solutions and all that kind of particular solutions. But I'm hoping you remember this. You have a second order ODE, the general solution is a linear combination of two linearly independent solutions. And if we're thinking of this as a function of time, in order to find the solution for all time, we can't just specify what the value of the solution is at time t equals 0. We also have to determine what the rate of change of the value is at time t equals 0. Okay, I can't just specify the initial value of the function. I have to specify its initial value and its initial derivative. Okay, contrast that to a first order ODE. These are kind of the simplest one, first order linear ODEs. There's only one linearly independent solution, and that means there's one unknown constant, and we only need to know the initial position of the function at some initial time to determine its value for all times that follow. Okay, what does that mean for us in terms of PDE? That means for the classical wave equation, which has a second order time derivative, for each value of the wavelength or the wave number, we have two linearly independent solutions. And we can either write those two solutions as a linear combination of cosines and sines, or a linear combination of the two different traveling wave exponential terms. Doesn't matter which one we use, okay? And because it's second order, we can't just specify the initial wave shape at time t equals 0 and expect that to determine the behavior of the wave for all time. So for example, suppose I say, I have a guitar string, right? And I took a photo of it at time t equals 0, and the guitar string was completely flat. It wasn't bowed up or down, didn't have any wavy shape at all. It was completely flat along the line 0 all the way to the ends where it's pegged together. Why wouldn't I be able to say that as time goes on, it's just going to stay flat? I took a photo of a guitar string at time t equals 0, and the photo shows that it's flat at that instant in time. Why can't I conclude that 1 second later it's necessarily going to be flat? Makai?
Because you don't know if before that it was already moving. It's just like at that.
Yeah, I had a little trouble hearing you, but I think it's that you said we don't know that the different parts aren't moving, right? Maybe the string was flat, but maybe one part of the string was moving up. I couldn't see that from the photo. The other part was moving down. In other words, I can't just know its initial position. I also have to know which way the string was moving at that point, right? If I have a standing wave, strings going up and down, there will be times when the string is completely flat, but it's on its way to another kind of node, anti-node situation, okay? So we got to know the initial shape and the initial rate of change of the shape. Contrast that to the time-dependent Schrodinger equation, which has that first order time derivative. In this case, for each k, there's only one linearly independent traveling wave solution. I don't have both the kinds of complex exponentials. I don't have the e to the I kx minus omega t and e to the minus I kx minus omega t. Only one of them comes in, the one with the plus sign up in the exponent there. And that means that the cosines and sines aren't going to be solutions because they would be linear combinations of both of those. Only one of them is a solution. Equally importantly, we only need the initial shape at time t equals 0 to predict the future wave shape. Unlike for the classical wave equation, for the Schrodinger equation, if you know the shape at time t equals 0, the shape at later times is determined for all time because it's first order in time. So those are just some differences between the classical wave equation. Despite the fact that they're both wave equations, they both have traveling wave solutions for every wavelength. They're different this way, both in how we need to specify the boundary conditions and how many linearly independent solutions form a general solution. Okay, so that was just a little, we want to keep that in mind as time goes on. The fact that this is first order in time, even though we call it a kind of wave equation, it's different from the classical wave equation in that we don't need to consider the initial velocity. If we know psi at time t equals 0, it's determined for all later time just by forcing it to follow the time-dependent Schrodinger equation. Okay. Okay, I know there's a lot, especially without me writing stuff on the board and doing it all on the slides here, but so let's go back and just review to make sure we know what the story was. What is Euler's equation? I'm not going to wait for you to call it out, but Euler's equation is e to the I theta equals cosine theta plus I sine theta. We are going to be using that periodically through the term to relate complex exponentials to cosines and sines. And we had actually 4 different forms of Euler's equation: the e to the I theta, the e to the minus I theta, and the cosines and sines solved in terms of those. They're all justified in being called that. What's the effect of in a complex traveling wave of increasing k? That causes the wavelength of this, we could envision it as a corkscrew-shaped function that's traveling with respect to time. The corkscrew is traveling down the x-axis. If we increase k, we make the wavelength shorter, so the curliness gets more tightly curled than it was before of that corkscrew. Okay. What's the effect of increasing omega? Well, I can see as omega becomes a bigger positive constant, I'm subtracting a larger, for a given t, I'm subtracting a larger number off. So that's going to cause it to translate more quickly down the x-axis. So bigger omega cause it to translate more quickly. But when it translates more quickly, it also looks like it's rotating around the x-axis. So sometimes you can see it both ways there. But for us, let's think of it as translating right now. What's the important consequence for the solutions to the time-dependent Schrodinger equation that it's first order in time? The fact that there's only one linearly independent traveling wave solution, and that we only need to specify the initial shape of the function to determine what its shape should be for all later times. That's not true for second order time derivative partial differential equations. Okay, and similarly for the classical wave equation, it's second order in time, means we have to specify the initial shape and the initial vertical velocity of that shape. We don't have to do that for the time-dependent Schrodinger equation. Okay, good. Almost done now with the introductory material. Any questions before we go to the last item, which is adding a little bit to Griffith's, just writing down the time-dependent Schrodinger equation as a postulate on paragraph 1 of page 1. Okay, hearing no questions, let's go on to that. Where does it come from? How can we sort of justify it? And some of the stuff we've been talking about is going to help us think about this here. How did Schrodinger come up with this? So I'm no expert at the history of quantum mechanics, but we used to have a real history of quantum mechanics buff who was taught physics and chemistry at Center. His name was Ed Montgomery, and he learned a lot about the history of the development in the time of the development of quantum mechanics. And he told, I'm just sort of paraphrasing here, supposedly one of Schrodinger's colleagues was poking fun at him, saying something like, you believe de Broglie's hypothesis, you keep believing that particles are waves. If they're waves, there's got to be some wave equation that those waves satisfy. What's the wave equation? And Schrodinger, feeling like he was a little bit under attack, searched very hard to find the wave equation that they satisfied, and it ended up being probably the greatest discovery of his life. Certainly the one that people are most familiar with his name from. So like Griffith's, many modern quantum mechanics textbooks treat this time-dependent Schrodinger equation as a postulate and ignore where it comes from and just say, it's just postulate. You can't find out anything about it. But of course, Schrodinger got it from somewhere. And so we want to be able to at least have an inkling of where Schrodinger looked to find his partial differential equation. So we're going to start with de Broglie's hypothesis. This predates Schrodinger coming up with this. De Broglie said, well, there's a relationship between wavelength and momentum. Here I'm going to write it as a relationship between wave number and momentum. K is 2 pi over lambda, but let's write P equals h bar k. Hopefully that's burned in your brain from modern physics. And this is like E equals h nu, but I've expressed it in terms of h bar. So E equals h bar omega is the relationship between the energy of a massive particle and its angular frequency, according to de Broglie. Okay. Now, here's where Schrodinger comes in. He says, let's treat non-relativistic particles. So if we're talking about something that's non-relativistic, it's free, so there's no potential energy, and its total energy would be, we'll go to the case where there's potential energy later on, but its total energy would just be its kinetic energy if it's a free particle. And if it's non-relativistic, that can be written as p squared over 2m. So Schrodinger says, I can substitute de Broglie's relationships in for P and E, and I can get a relationship between K and omega. Let's substitute those in. Substitute these into just E equals P squared over 2m for a free particle. That gives h bar omega equals h bar squared k squared over 2m. And that is a dispersion relation. Notice it's a relationship between omega and k. It's going to tell me something about a phase velocity of the waves that have associated wavelengths here for traveling wave solutions to something. So we sort of started out earlier with a wave equation, and determined what the dispersion relation was. Here, Schrodinger has a dispersion relation, and he wants to sort of go backward and say, well, what kind of wave equation could this have come from? So let's try to go backward and think about, if I have a traveling wave of this particularly simple form, this complex traveling wave here, e to the I kx minus omega t, what sorts of partial derivatives would I need in the wave equation that this is going to satisfy, so that when I substitute this in, I'm going to get this dispersion relation? That's what Schrodinger is doing to try to get at this, okay? So the question is, if I substitute this in, if I take a single, notice there's only a single power of omega on this side. That means if I want to pull out a single omega factor, I better take a single derivative with respect to t. That means my partial differential equation better be first order in t. So if I, just to experiment, if I take d psi dt, the chain rule gives me minus I omega times psi back again for this traveling wave psi solution. And therefore, if I want to end up with an h bar omega on this side, I could divide both sides by minus I and multiply both sides by h bar. I h bar times d psi dt is h bar omega times psi. That's going to pull out the right thing. This combination of derivative and constants is going to pull out exactly what I want on the left-hand side for the dispersion relation. Similarly, if I want a factor of k squared to appear on this side of the dispersion relation, I better be taking 2 x derivatives of this. So let's just experiment. If I take the second x derivative of this function, the chain rule says you got to pull out a minus k squared. I didn't want a minus k squared to appear out in front. I wanted an h bar squared k squared over 2m to come out on that side, but I can then multiply by h bar squared and divide by 2m and multiply by minus 1. And that tells me that this combination of constants in front of the second derivative gives me what I want on the right-hand side. And therefore, if I substitute this into a partial differential equation that is this equal to this, hopefully I've got that written down here, then I'm going to get the dispersion relation, which is equivalent to E equals p squared over 2m and de Broglie's hypothesis there, okay? Now, there are other higher order derivatives that you could have put in here, but Schrodinger realized that this was the simplest one that you could write down that gives the correct dispersion relation, has the lowest order derivative. So he just postulated that as the simplest one, and it ended up working or being consistent with experiment later on. Okay, so that's for free particles. Schrodinger says this is going to be the wave equation that psi has to satisfy if I want my dispersion relationship to be equivalent to E equals p squared over 2m and p related to k and E related to omega in that way. Okay, now the problem is, so we've got the free particle time-dependent Schrodinger equation, but now what about for particles that are moving around in some potential energy function, maybe a harmonic oscillator well, or some other interaction with some other particle that gives a potential energy function? What are we going to do? Well, so in mechanics, we usually specify a conservative interaction, and in quantum mechanics, particles down at the microscopic level, the atomic level, every interaction is completely conservative. So we can specify forces via potential energy functions. And in this course, I assume it's the same in your modern physics class, we denote that by a potential function that's given the symbol V, V for potential energy. Sometimes in mechanics, it's given the symbol U, but here in this book, we're going to use V as the potential energy function. So for us, since we're just talking about X in one dimension, V is going to be a function of X. We'll assume it's not a function of time for right now. Okay, so how do we have to adjust the derivation that we did before? Okay, well, de Broglie's hypotheses are going to stay the same, those postulates of the relationship of momentum and energy and the wave properties of the wave. But we're no longer talking about a free particle. Now we're talking about a particle that might be moving around in a potential energy function. And so the correct relationship is The total energy is the kinetic energy that we had before, plus the potential energy. And therefore, when I plug these into this relationships, I get a slightly more complicated relation. That's my dispersion relation. And I want to go back and adjust the partial derivatives, or adjust what I'm doing here to actually take into account that when I substitute this traveling wave solution into there, I get the right dispersion relation. And if you do that, you'll find out that the correct equation only has to be altered by an additional factor of v times psi appearing in that equation. So again, this is what we call the time-dependent Schrodinger equation, and it's the simplest, that means lowest order derivative, partial differential equation that gives a dispersion relation that's consistent with de Broglie's postulates. Okay, and that's kind of the starting point for the rest of the course. Griffiths postulates this on day one. You're familiar with it somewhat from modern physics, but the rest of the term is, a lot of stuff that you went through in modern physics, but we're going to go through it in much more detail. Learning how to solve this wave equation for waves in the presence of various potential functions. So we're going to do many of the same problems you did in modern physics. Of course, problem one is the infinite square well kind of potential function. Then slightly more complicated, or quite a bit more complicated analytically speaking, is the harmonic oscillator solution, which I assume you did in there. We'll talk about free particle solutions where v of x is just 0 for all time. That means a particle with 0 potential energy that it's moving in. And it turns out that's quite a bit more complicated to describe for reasons that we'll get into in chapter 2. Okay, we also have to learn how to interpret wave functions in terms of experimental outcomes. You know this from modern physics, that just because you know the shape of a wave, what does that mean in terms of the outcome of an experiment? That means that you have to take the magnitude squared of that psi and interpret that magnitudes of psi squared as a probability density function. So we're going to keep doing the same thing in this course. And also, we want to, along the way, connect it with what we already know from classical physics, right? We know that if you take a classical point particle and put it in a harmonic oscillator potential and let it go from one side, it's going to oscillate back and forth, right? If it's in a harmonic oscillator potential energy function, it'll oscillate back and forth. So when we solve the time-dependent Schrodinger equation for the harmonic oscillator potential, we ought to at least be able to see that in some limit, when the wave should be behaving more or less like a classical particle, that we can see that oscillation back and forth, and we will make that connection in the course. And so starting tomorrow, we're going to go on to the book, but just to not do too much on Zoom on one day, I think I'll stop there and we'll start fresh with chapter 1 tomorrow. And I'll probably start by maybe just addressing a couple of the reading responses associated with what we've been talking about in this introductory material. And then after we get into the first sections of chapter 1, I'll address some of your reading responses from the chapter 1 sections that you're supposed to be reading now. All right, I know that was a big information dump, but I'm hoping that, 2/3 or 3/4 of this is all familiar. It may not be on the tip of your tongue, but you could follow the story without too much trouble and bring back some of those things that were distant in your brain to the forefront so that we can connect with them. Dispersion relation, we're going to be talking about group velocity and phase velocity, which I assume, talked about in modern or in waves. Same thing, we'll connect up with that later in the course here. Any questions before we